So again, cyclohexane is a very stable ring structure. It is found very commonly in nature and in natural products. Part of the reason why cyclohexane is so abundant in nature is due to its ability to adopt different configurations to minimize torsional and angular strain. The lowest energy conformation is known as the chair conformation, and that's what we will be talking about today. Cyclohexane has no ring strain in the chair conformation. No angle strain because its angles are about 109.5 degrees, and no torsional strain because all adjacent carbon-hydrogen bonds are in the staggered conformation. The other possible conformations of cyclohexane have some amount of angle or torsional strain. This is the only one that has none. So how do we draw a chair conformation of cyclohexane? Okay, there are several ways, and it does take a little getting used to, but this is the one we're going to work through. First, you're going to want to draw a wide V. Second, draw a line going down at an angle of about 60 degrees, ending just before the center of the V, as you can see here in step 2. Okay. Then draw a line parallel to the left side of the V, ending just before the left side of the V. Okay, so again, in step 3, you can see we draw a parallel line, and it's not quite as long as the line that we are drawing the line parallel to. Draw a parallel line to the line from step 2, going down exactly as low as that line, and then finally connect our last 2 dots. If drawn correctly, the chair should contain 3 sets of parallel lines. Now, once the carbon skeleton has been drawn, we draw out the other 2 bonds that each carbon of the ring should have. Each carbon in the ring has 2 substituents. One is in what we refer to as the axial position, and the other is in the equatorial position. Adding the axial substituents is fairly easy, okay? They point straight up and straight down, alternating around the ring, all right? So generally, we always start with the top right-hand carbon and draw a line pointing up. Then simply go around the ring and draw lines pointing down and up, alternating all the way around the ring, as you can see was done in this example. The second bond you're drawing is the equatorial bonds, all right? And this is a little bit more complex. In the equatorial group, you are drawing the line going off of the ring, so away from the ring, and they run parallel to the lines of the chair. So once again, let's start with our top right-hand carbon. My equatorial bond will be pointing towards the opposite direction of whatever my axial bond was pointing towards. So my axial bond for that type right-hand carbon was pointing up. My equatorial bonds will be pointing down, and it will be running parallel to this line right here, as you can see, okay? My second carbon was had an axial bond that was pointing down, right there, okay? And so my equatorial bond will be pointing upwards, and it will be running parallel to this line right here, okay? You can see that I'm pointing them away from the ring, not in towards the wing, away from the ring in the opposite direction that my axial bond was pointing in. Once you go around the ring and get them all drawn in, this is what your ring should look like with all of the bonds drawn out. Now, when cyclohexane has one substituent, there are 2 possible conformations. You could have your substituent be in the axial position or in the equatorial position, okay? Ring flipping occurs by rotating all of the carbon bonds in the ring. And when this occurs, axial substituents become equatorial, and anything that was equatorial becomes axial. So as you can see in this ring flip, my carbon, my first back carbon that had my X substituent in it, kind of moved around, and now it's in a different position, and all of its axial bonds have become equatorial. And even though they're not drawn out, all of the equatorial bonds became axial. So let's consider methyl cyclohexane. Okay, that is cyclohexane with methyl group. The chair conformation where the methyl group is equatorial is much more stable than the chair conformation where the methyl group is in the axial position. So at room temperature, about 95% of methyl cyclohexane exists with the methyl group in the equatorial position. And this is due to steric interactions that destabilize groups being in the axial position. Okay, on our next set of slides, we're going to be kind of working through drawing out cyclohexanes, monosubstituted and disubstituted. For now, what I want you to keep in mind is that groups, any kind of attachment substituent on a cyclohexane group is more stable when it's in equatorial than when it's in the axial position. If you have more than one substituent on a cyclohexane, the most stable conformation will have the larger substituent in the equatorial position than in the axial position. And we'll work through one of the skill builders in the next set of slides to look at that.